Hello everyone, and welcome to this talk on Ravenna and AES67. Let's wait for 1 more minute to the last members. Okay, so let's start. So this is a talk about Ravenna and AES67, about the basics of the protocol standard and the interoperability with Dante. So I'm Nicholas Sturmer, and I'm working now for Merging Technologies. I'm active at the AES, also was, but not so much right now, active at the JTNM, the Joint Task Force on Network Media. I'm giving training at the CFPTS in France, and I used to work for Digigram as well. So I'm interested in the AES67, ST2110, and of course the control of systems. So this one was not translated to English correctly. I'm obsessed about Linux, the cloud, and M&Ms, and I used to be a sound engineer, signal processing, and working at the CNRS. Let's start by presenting Merging Technologies. So Merging Technologies is 30 this year. So happy birthday, and you can see here the first place where the actual company was placed. So Merging is producing and selling software and hardware. So the software is Pyramix. We also have Ovation, and the hardware, the rest coming in the range is the Anubis unit. We also have the Merging Oris and Happies, and the NADAC for very high quality audio. So all those devices are using audio over IP, which means that every connection coming and going through this device can be made using the network. So why audio over IP at Merging Technologies? The first advantage is connectivity. With audio over IP, you plug and play with much more simply, and with only one physical medium, for instance, the Ethernet cable, to transport both clock and audio. Audio over IP also allow high sampling rate with no constraints at all. When you're using AES3 or when you're using MADI, you can be limited in the sampling rate. With audio over IP, the only limit is your own imagination. You can also have a high number of channels. So this one, of course, is limited by the overall bandwidth of the Ethernet that you're using. But with a 1 gigabit Ethernet, you can really, even in DSD or DXD, you can go above hundreds of channels. And of course, it's using long cables that can run long distances, so up to 100 meters. And the network provides easy management and a lot of modularity. So for instance, we have customers that are buying one OS and then stacking other OSs, and they see the whole network as a single input and output metrics for their Pyramix or whatever, or the digital audio workstation they are using. And of course, we have the last addition to the whole merging lineup, which is Z-Man, which is a card that is aimed at OEMs to easily allow AES67 and RAVENNA compatibility into an existing devices, for instance. So just by using I2S, you can go get audio or put audio into the Z-Man and it goes out to the network. But how is it done? What is AES67? What is RAVENNA? And what's those ecosystems? What is the standard? And what is a network? Or may I say, what is an AES67 network? What is this? Its specificity. So first, let's talk about standards and protocols. So audio over IP is there for a long time now, for more than for almost 20 years. It started with audio over Ethernet, and most of you may know already Ethersound or CobraNet. And from the beginning, the benefit was a higher bandwidth and an easier distribution using the network. So instead of having the big multipliers that you would run for tens of meters and that would eventually break with a lot of copper wires, you are just using one Ethernet wire that costs almost nothing. And of course, the problem was that every manufacturer came up with its own standard, with its own protocol. So in 2013, the AES67 was published. So why AES67? So the goal was to avoid one more protocol. And it's the same joke over and over again. You have, for instance, 14 competing standards, and then someone has this very bright idea of saying, let's try to put all the standards in one, and eventually you end up with 15 different standards because all the manufacturers, they cannot cope with the need of the standards, or they don't agree with what's written in it. So the idea with AES67 was to find the most common denominator in all the pre-existing standards. So the standard committee was started in 2010, and with most of the big leaders in the by then audio over IP ecosystems. And the idea of AES67 was, well, if you are equipment manufacturers, you probably want to keep discovery and control and monitoring with you, with your own ecosystem, with your own way of discussing between the equipments on the network, because it belongs to the way you are doing business and the way your customers are accustomed to using your different devices. So AES67 focused mainly on the lower layers on the network, actually the lower layers of this model here, and trying to push everyone higher by trying to get to use the most recent protocols. So the one thing I didn't say is that if you have questions, you can ask it in the chat anytime. Let's try to make it more interactive as possible, even though with YouTube it's not that symmetrical in terms of interaction. When I did these talks yesterday in French, it worked very well. So you have a question, just ask it on the chat, and let's make it a little bit more live than just a simple webinar. So the goal of AES67 was interoperability, and the idea is always the same. You run a live event, and your live event is using Dante, for instance, and someone is coming on to do captation, to do a capture of your event, but it's using a Ravenna system. And then how do you get, what do you do to exchange streams between the Ravenna and the Dante ecosystems? Well, you're using AES67 actually. So this is true for most of the different audio over IP systems. And on top of that, AES67 is built on the view of having the most robust systems and the most interoperable one. So there's one interesting topic, which is the difference between Multicast and Unicast. So AES67 is mainly based on Multicast, but not necessarily. You can do AES67 using Unicast, but Multicast has many different advantages. So, for instance, the control of bandwidth, because Multicast will only send one packet at a time on every branch of the network. So you get much more available bandwidth for your different streaming. Also, the distribution is controlled by the network, which is you are using the switches and actually the core of the network to do your distribution and your stream distribution on the network. And this is more robust than Unicast because of the very first way the different switches are working. So if you are sending a stream to a device and this device disconnects from the network, if you're using a Unicast stream, the device that is sending is actually sending to the device. And because the device goes away from the network, the switches, they don't know where to send it, and they end up eventually sending it everywhere on the network, just in hope that someone would know where the actual device is. So this is a kind of flooding, and with Multicast you avoid this thing by by asking the devices to request a stream. And when they are not there, the stream is still on the network, but only sent to the actual ports of the switches where the stream is actually needed. So how does Ravenna get compared to AES67? So Ravenna was actually developed before the launch of the AES67 standard, even before the beginning of the working group X192. But still, it continued evolving with the writing of the AES67 standard, taking from it the most recent protocols and the most clever choices. So actually, Ravenna, which is mostly used in broadcast, by the way, is more complicated than Dante. And this mainly comes from the use of Multicast, for instance, which requires the switches to be correctly configured. But it's also fully compatible with AES67. So it's only it's a kind of AES67++ that has added connectivity, and it ends up being a full solution with even initiatives like the ones I will show you tomorrow that are trying to complete it. When it's in its own, Ravenna is a fully working solution, and quite a good one actually. So here is the difference between AES67 and Ravenna. Okay, so the difference between AES67 and Ravenna. So you see that AES67 is using those, I have the habit to say, 3 pillars: PTP, HMP, and QoS. Ravenna is adding the discovery part. So if you remember, in the most common denominator, in AES67 I said, let's put discovery out of the system. But discovery is the easiest way to do connection management between the devices. So Ravenna is adding this layer, and also adding, so there's no unified control specified in Ravenna, neither is there in AES67, of course. Control is often tried to be specified with standard, but they never really work. So yes, we'll talk more about that tomorrow. So there's a question in the chat. Is it possible to use VLAN with AES67? Yes, of course. So as we will see later, AES67 is a full IP compliant protocol. So you can use any IP technology or even layer 2 technology that transports IP that you want. So you can have AES67 on something other than Ethernet, for instance. You can have AES67 on, I don't know, I have nothing in my head right now, but it's really a layer 3 problem. VLAN are layer 2, so any type of VLAN is compatible with AES67. Yeah, so that's a question, Tibor. So since the control is not specified at all, the way of controllers work or interact in the network, it's not a question for AES67 actually. AES67 is really at another layer of the network. So the controlling side, we will talk about it tomorrow, but not to provide solution, just to show what's offered in terms of merging products, and just as a just to show the different problems that are posed there. Right now, today, so we will talk about what is actually in AES67 and Ravenna, and I will show you some demos as well. So let's go. So here I have my network. Here it's my home network, or actually it's my work network, but I'm connected to it using VPN, so those are my home device as well. We have 4 different switches. So those 3 merging named switches are Cisco switches, and this one is a switch from Artel. And you see that some devices are double attached. They have 2 different Ethernet ports that are plugged to different switches. And you can see also that if you select a switch, you can have the different bandwidth. And if I select a stream, I can see that this stream is actually coming from 2 way on the network and getting nowhere. So let's do a connection to check with the different switches. What is the best way to run AES and Ravenna stream between VLANs? So that's a good question. So routing between VLANs. The best way is to have a fast router. And because it's multicast, you want to have a fast router that does multicast. So this is the only thing that you need to know. And later in the talk today, we will see more about multicast and the different things on what is using AES67. So maybe I will answer your question more later. So you remember I showed the Horus product before from Merging Technologies. So this is the first web page that you get when you try to reach your Horus on the network. So the Horus is actually this device there. I think it's the same number. Yeah. And those are not the Ravenna pages or what we call advanced pages. You actually have to go to another page on the device, and you enter into the advanced configuration. So AES67 compared to Ravenna, since it doesn't have the easy configuration of Ravenna, it's more an advanced thing. And even at merging, we have a lot of tools that try to ease the connection between the devices. Most of the tools are only working with merging devices. So if you are using on a network different vendors and different devices and try to exchange streams between them, even with Ravenna, you have to use these advanced pages. So for instance, I can create a source. So I push the button, create session, and I can name it. So I can name it April 8, 1. Okay. I can choose the Unicast address. So a Unicast address is a special type of Unicast IP addresses. So on all the IP addresses, there's a specific range that is kept for the Unicast addresses. And you can set it either automatically or you can set it manually if you want to choose a specific address. You can also set a different number of parameters manually, and you can set the number of channels you want on your stream. So now I want to connect my stream to another device. So let's choose, for instance, the Anubis. So I have an Anubis on my network, and same as before, this is the pages that you will go to for the at first when you try to connect to the device, and those are the advanced pages. So this time I will go to sync and try to connect, and because we do Ravenna, we have the chance of having this discovery that is on the network, so I can find all the streams that are available on the network, all the Ravenna streams and some AES67 streams, and I see my streams there, April 8 that I worked before, that I created before. So that's as easy as that. I chose my stream, I connected the device to the stream, and the device says, okay, session status connected, receiving RTP packets. So just knowing the different acronyms there is another problem that we will get later, but everything is green, so that's already a good thing. Yes, so cool. That's analog. Those are good questions that I will address later, and most of them will be addressed tomorrow as well. So if we go back on the network and we choose the streams that we just created, so that's why. Okay, yep. Here I can see that this comes from the Horus here, and it is distributed to the Anubis. So with this kind of software, I can trace the stream on the network and see where it's going. And you see that because it's multicast, other devices can see that too, if they are registered to subscribe to the stream, and other parts of the network are not receiving it at all. Okay, so the other devices are not receiving it because they didn't subscribe to the stream. The source ports, yes. What about the source ports? So the source ports, those are, I think you are making a reference to redundancy. Redundancy, it's not on the talk today, so I'm using right now only devices that have only one port. So the source port is irrelevant there. Okay, so actually connecting with Ravenna is quite easy. We will see that with AES67 it's a bit more complicated, and we will have a demo later on that. So how do we check that everything works? You write a standard, and your only hope is that every engineer in the world, actually every engineer in your business, will understand the standard the same way as you've written it. And even though in the standard group we are many, it doesn't work that way, because the way the text can be interpreted is always complex. So behind the standard document we did ClugFest, where we gather together and we try to plug every equipment to another. And there we did a good deal of debugging from everyone. We also distributed the PICs, which I will talk about later, and the PIC summary. And the PIC summary is a really great tool for knowing what a device can do before buying it. So right now, when you are trying to find an AES67 devices on the network, or at your reseller actually, you should look at the PIC summary first, and I will tell you later what to expect from those PIC summary and how to use it. And of course, you have the different test programs. So maybe you heard of the JTNM badges, like this one. Those are going to be more and more used, and they are really neutral qualification of the device that gives you a neutral view of the actual performance of the devices. And of course we have users and a lot of problems of interoperability, so the fact that you can actually send audio to another devices on the network that is not from your own company. Some of those problems are of course solved, put right on by the user, and this is perfectly normal. AES67 is only 7 years this year, and it's really young for its standard. So it's a technology that really has to be improved, and that has to have some beta tester, or at least early adopter. So getting back to the demo to answer the questions from Tibor, the audio port on the source. Yes, so be it on the source or the destination, the audio ports are selected here. So here you choose one of the inputs, for instance, the analog to digital card, number 3. And here it's an 8-channel card. So if I send the whole 8 channels, nothing special to do. If I want only to send 2 channels, I can select the pair here. For instance, 5 and 6, and I click to apply. And this is how I select. Yeah, so I think this is your question. And then on Anubis, it's another way to do it. Because we have an internal matrix. So here I changed my stream to 2 channels, so I have to apply 2 channels as well. And I can select the output channels with this routing matrix, so I can even have the same input streams feeding different outputs. So I hope this answers your question, Tibor. Okay, so there's not only AES67 but also other protocols. So AES67 is based on interoperability, but it's a damn good protocol. And at the SMT, when they tried to go beyond the ST2022, which was SDI over IP, the problem with SDI over IP was that even an audio device would have to be fed the whole SDI stream to be able to just extract the audio channels. And this is obviously problematic because when you try to do 4K, you are easy, of course, above 1 gigabit, but even over 10 gigabits of data per second. So they needed to separate the audio, video, and metadata streams. And well, so they had this new standard ST2110, and they said, well, AES67 is already written, and it's a damn good protocol. So let's use this standard to do the audio transport of ST2110. So of course that they added some salt of their own to the definition of ST2110, but mainly we can see that ST2110 does fit within AES67 with a bunch of different constraints that I will not explain here. We can talk about it tomorrow. Which in turn means that every RAVENNA devices on the network, on the market, and most of the AES67 devices on the market, they are straight on compliant to ST2110. So this is the only thing that you need to remember right now. And of course we have ST2022-7. So the idea is that you cannot trust the network. So in the 80s or late 70s, when the network was, when the idea of the Ethernet network was brought up, the idea was that you define a network by knowing when you put a packet inside, but not by when you get the packet, you actually get the packet, or if you actually get the packet out of the network. So this is really problematic when you're trying to do real-time audio, because not knowing when or even if I get audio from the network when I did send it at the right time, that's a problem. So thankfully today we have really fast network and it doesn't happen anymore, but shit can always hit the fan, and you may have a problem in a switch, or somebody unplugging a cable, or a cable getting broken because it's badly plugged, etc. So the idea of ST2022 was to double the stream on two different passes. So they can be, the passes can be on the same network, as opposed to Dante, which I think requires two different networks to do redundancy. Here we can do redundancy in the same network, at least on the physical level, but even on the IP level. So right now, what I'm doing on my own network, what I showed you before, and so you are secured, because even though you are losing one packet or a stream of packets on one side or the other, you always have the other side to be there as a backup. And so this is also named streamless redundancy switching, which is no matter what happens on network one, on path 1 and path 2, if I get at least one packet each time, everything is fine on the network. So those acronyms, AES67, ST2110, and ST2022-7, those are the main three ones that you will see when doing interoperability and audio over IP. And depending on if you're doing live shows or you're doing broadcasting, you might get more from the ST2110 side or more from the AES67 side. So let's go a little deeper and define how it works. So as I said before, AES67 is based on three main principles. You have transport, you have clocking, and you have stream description. And actually, the more important is the clocking. The clocking on the network is how you do share the same time between the devices on the network. So this is useful, of course, to have the exact frequency. So instead of sharing a word clock on the network, you share the PTP time, and you can reconstruct the actual media clock, which is the audio clock, 48K or 96K or 352K. But you can do more than that, and we actually know the exact time up to a nanosecond or tenths of nanoseconds where the audio was sent on the network. And so you can synchronize the audio playout on different devices on the network based on those time. So let's see. Before the demonstration, so there are PTP switches, and they are useful, but they are not always needed. And we did some installations with really basic Cisco switches without any of the PTP capabilities, and systems exchanging more than hundreds of channels in DXD and with no problem at all. So it really depends on what you have on the network, how you use your network, and the expectation that you have in terms of precision of your different clocks. But one thing is clear is that you have to check for masters, PTP masters and elections. So on a PTP network, you define what master should be, or you can let the PTP system select itself the best master for your system. I will show you how to do that right after. You also have to check for topology, and better have a master that is near the root of your network, so that you have passes that are mostly the same everywhere. And look at 1-step and 2-step. And this one we will see a little more tomorrow when we do captures on Wiretrack. But the basic is that you have to always check a device before putting it on the network. It's really easy, and trust me, I did it dozens of times, to mess with the network by adding a device and having it not properly configured. So this is the thing that you have to check and to be aware of when you are actually using PTP. So let's see how this works. Here I have a device, which is the Anubis, and the Anubis right now is a master. It's a master on the network, and we see here the master reference, the GM ID, the ground master ID, and here the statistics. But those statistics they give a kind of the feeling of how the device is ahead or behind of time from the master. And of course, since this device is the master, there are no use for that. And here you have the different parameters on the network. So this checkbox, for instance, is really useful, and it's a checkbox that is used to constrain the device to be only slave in terms of PTP. So if I check that, the device will lose its master status and will begin to be listening. And a listening device is a device that is waiting for announcers from the masters. So when the master disappears from the network, every device that feels like it should be the master is sending a packet, an announce, with its different parameters, and the device with the best parameters wins, and all the devices do sync it to that. So here we have the information that it's the device 130590 that did pass master. So a device did take over the role of master on the network. And if I go on my Dante clock status, yes. So this is it's actually the Dante device that took over the role of master. I can always also do that. So mainly the thing that you have to care is the value of priority 1, and set it. The lower the value of priority 1 is, and the higher the chance of it being master will be. So if I set to 250, for instance, 250, the device will not be master, even though slave only is not checked. The actual Dante devices on the network has a PTP setting of priority 1 that is lower than 250, and so this device is not taking the role of master. If I set it on a value that is lower than the value of the Dante devices on the network, then boom, it just switched to master, and Dante device here just switched to slave. So this is how you do actually an AES67 setup. My advice is that on an AES67 setup you should first use select yourself a set of devices that might be masters and give them the appropriate priorities, like main master, backup master, etc. And all the other devices, try to have them by being slave only, either by checking the slave only button here, or by having the priority set to the highest value, which is 255. Once you do that, you can also control the way the audio is played. So audio is put on the network into packets, and those packets, they are sent every here we have 40 samples by packets, I think. No, we have a quarter of milliseconds packets, so we can go as low as 2 quarter of milliseconds, so 1/2 millisecond in terms of buffers, if we want to. So I can check that. I can force my Unibase to go into this mode. And my thing there is okay. So, and this is the player delay, and the player delay is the buffer on which I will put the different packets when I get them from the network. So the bigger the buffer is, and the better the buffer, my receiver is able to cope with different changes on the network, so jitter or longer path, etc. So for instance, we have customers that do transatlantic or transcontinental connections, AES67 connections. So those connections, they will not be made in transporting the data in less than a millisecond. So we have buffer that can go higher than 100 milliseconds. So here I can choose 42 milliseconds, and this means that if the audio is sent on the network at time 0, it will end up being played by the Unibase 42 milliseconds later. It's actually the latency. And if I put 96, I will get to play it 2 milliseconds later. And if I put 24 here, 24, it's actually played half a millisecond later. So the lower the buffer, the lower the latency, but also the higher the risk of losing a packet and therefore losing audio is on the network. So it depends on your application. If you want to do live shows and live events, try to have it down, but if you're only doing recording, try to having it as high as you can bear in terms of interaction, so that you get a higher chance of not messing with the network. Of course, the network never fails except when you don't want it to fail. So it's just a security measure, and it doesn't mean that it doesn't work at 0.5 milliseconds. It's just that in terms of security, it's already best to have the best behavior. Okay, so that's it for PTP. Then PTP and Dante. So there's a problem with Dante, and the problem is that it's the leading standards. So we and every AES67 manufacturers has to cope with different Dante protocol. Just so the question from Tibor, is the sync latency independent of the source latency? Yes and no. So you have to have a minimum latency, and the minimum latency is actually 3 times or 2. If you do the thing right, you can go down to 2, but the basic in AES67 is required to be 3. So you can go down to 3 times the packets. So it's not really a latency per se, but you see that I'm sending a packet from the Horus, which is a packet that I have to go there to see, has 12 samples. So it's a packet of 1/4 of millisecond. And on my Anubis, I cannot receive it if I have a buffer that is lower than twice the packet time. So if I have 20, but you see, it has corrected it. So it will not even accept it to be 24. So in this way, because you have to have a minimum time that is twice or 3 times the sender packet size, the sink latency and the source latency are linked. But it's only a minimum. The maximum is not actually not linked to the sender latency at all. Okay, so back to Dante. So Dante is using PTP v1, and they chose to, for whatever reason, that they would keep PTP v1 even in the in all the AES67 devices. This means that when you do a exchange AES67 between a Dante device and an AES67 device, one of the Dante device will act as a boundary clock, which is a clock that is a boundary, a frontier between the version 2 and version 1 version 2 and version 1 PTP, and just sharing the same time. So in this document is very clearly explained. So the Dante acts at a boundary clock, and this means that one Dante equipment will be slaved to PTP v2 and act as a master to PTP v1. So this is a demo I cannot do today because I have only one Dante device on the network, but it's really straightforward. But pay attention of the clocking in Dante, and as I've shown you before, here, not this one, this one, you should check that this AES67 status is slave or master, and the primary status is master of the equipment that is slave or master to PTP v2. So PTP v2 is AES67, and primary status clocking primary status is PTP v1. So another question from Tibor. Will Dante move to PTP v2? I don't know. I hope as a backer of AES67, but it's their own program, and it's actually working great. PTP v1. There are slight differences between v1 and v2, and from what I know, when you're using Dante Domain Manager and you switching those Dante devices to ST2110 mode, they are using PTP v2 already. So you can see whatever you want there. You can see it as a way of trying to stick to what's already existing in the lower tier, because Dante Domain Manager is the higher tier, or just as a convenience. Then you have IGMP, which is multicast distribution. So when you use multicast, you accept the devices to be asking to receive the multicast stream. So you can actually configure the streams by hand, and those different routing done by the switches, you can do it by hand, or you can do it automatically, which is asking the devices, actually the endpoint devices, asking, well, send me the device from IP, send me the streams sent to IP, blah, 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 blah. And after that, all the switches in the path, they register that they have to send this device the stream, and they put it like that. And this is called IGMP, for Internet Group Management Protocol. And in those switches, they do IGMP snooping. That is, they see the packets, the IGMP packets coming and going, and they actually enable or disable multicast distribution on the stream. So, as a matter of fact, and as I showed you before, only the branches in the network that registered the stream will receive it. So this is a really efficient way of keeping the bandwidth also down, but also deterministic. That is, on the higher tier of your network, closer to the root switch, where everything is coming and going, it's easier to have a controlled and deterministic bandwidth by having the exact stream that comes and goes from the switch, and do not change based on the number of clients that are downwards the network. So there are 3 versions of IGMP, and the one you should care about is version 2. The advantage of version 2 is that you can not only register a stream, but also try to send a message that you don't receive the stream anymore, don't wish to get to receive the stream anymore. Before that, in V1, it was only a timer. That is, the switch actually asks repeatedly every 30 seconds or 2 minutes what are the streams that you are listening when you're a device, and you respond with those streams. And in V1, if you didn't respond past 2 questions, you would not receive the stream anymore. In version 2, you can do fast leave, which is you can ask the switch not to send you the stream anymore. So this is useful in terms of really big streams. For instance, you have 10 gigabit link and you have two 6K for 6 gigabit 4K streams, and of course you cannot receive 2 at the same time. So when you're doing switching between 2 streams, you want the stopping of the sending of the first stream to act as fast as possible so you can receive the second one. This doesn't happen really in AES67, so we use IGMP v2 in terms of compatibility, but most of the time we don't activate the fast leave option in IGMP v2. If you're using IGMP v3, you probably know or are working with people that know what they are doing. So no need to do that, but basically v3 is differentiating the streams not only by their destination address, so the address on which they are sent, but also from their source address, that is the IP address of the equipment that is sending. So we can consider that on my Anubis I have a source. I can create a source that has this IP, this multicast address, and when on an ORIS I try to create a stream with the same address, it's working. Okay, so it's working. So I can have 2 different streams with the same multicast address that are coming from 2 different devices, and of course this is problematic. So this is where IGMP v3 is useful. At merging, and most of the RAVENNA devices, they are using an automatic address distribution protocol that uses the device IP 2 last bytes for the address, so that it doesn't collide, that you don't have collision between the addresses that are chosen by the different devices on the network. Okay. And QoS. So we had 2 questions on QoS from Analog. So QoS is managing the traffic to have priority. That is, you have a priority tag on the packets, in the packets, and the priority is the packet is put on a queue in the switch based on the value of this priority tag. So the higher priority queue is the one that is looked at first when looking for a packet to send on the network. So this guarantees that you can define some packets to traverse the network, to go through the network as fast as possible, and some streams, some packets lower than possible. So Tibor, the address range is the only way to specify multicast or unicast. Yes, if you are talking about the first octet here, the first byte here, the 239, yes, those multicast addresses, they are in the range 224 to 240, and those are the only addresses that are allowed to be multicast. And the switch knows them, and the switch will only distribute them based on their actual multicast address. So you can try to mess up with the network. I don't recommend that, but you will most likely not be able to do anything fancy with multicast, with changing the very norm of using multicast on the IP address. So in QoS, the higher priority queue will get off first. So the question is, what do I put in the higher priority queue? What on my AES67 system, on my clock, audio, and control packets, which are actually the packets of me connecting to the device and looking for the HTTP server and the web pages from the device. What is the stream or the type of traffic that I will privilege and that I will put in the higher queue? So this is the clock actually, because if I don't have the clock, if I begin to lose the clock on the network, I don't care about audio because I will not be able to play it anymore. So in QoS, we'll go first with the PTP packets, then the audio, and then the control. So same as with Dante, if you already looked at a switch configure for Dante, and yeah, and I can show you on this Cisco switch. So this is a Cisco 350 that is configured in using the advanced mode. I can go to quality of service and DSCP to queue. And here I see that I configured everything on Q1 except some DSCP, so differential service coding, I don't know the P. And those are linked to the values, standard values of RAVENNA, AES67, and Dante, which of course are not the same. Why would they be the same? It would be too much easier and would not leave enough work for me to do as, for instance, in this webinar. So 56 is the PTP using Dante, 48 is the PTP using RAVENNA, 46 is the audio using Dante, and 34 is the audio using AES67. So the thing is that you try to get them to different queues or the same queues, because 46 is also the clock using AES67. So the way you distribute the different tags are up to you. And this is one way of configuring the switches, and this is the way that we send the already configured switches from merging. And you can always also, on most of the devices, you can also choose between different values of DSCP for either PTP or when you are streaming here and there. You can also choose for different value of DSCP for the streams. And the advantage here is that you can even choose different DSCP for different streams. So you can have priority streams, prioritize some streams against the others. For instance, you have a intercom, and you'd rather use your intercoms packets than your audio packets for your front field, for instance. So this is a way of doing the separation. But don't trust too much QoS and don't put that much hope on QoS. It's really just another security belt that you want to have it on the network, but you really don't want it to be kicking in, because if QoS is actually playing a role on your network configuration, you have much deeper problems than just QoS, because you are up to bitrate on some input ports that is much too close from the maximum, and the maximum might not be, for instance, on a 1 gigabit line, it might not be 1 gigabit at all, because it depends on the way the different devices are acting, and some devices cannot receive enough bandwidth to accommodate with the 1 gigabit. So it's really about testing and being able to see what works and what works not. So should I use QoS on my network? Yes, but don't really expect that you will see any difference. For instance, one thing that you have to know is that, okay, my PTP is on the first priority queue, but it doesn't mean that my PTP will be sent first, because if my switch is in the middle or beginning sending big packets, for instance, 1,500 bytes packets, it will not stop sending the packets to send the PTP that just arrived. It will finish sending these big packets and then send the PTP. So this can lead to delays of up to 10 microseconds on the network. So with PTP, you will not get precision higher than 10 or 20 microseconds just by using QoS. You also have to use other strict things, and for PTP it's all about the algorithms on the client side that try to nivel and limit the noise on the measurement to get closer as possible to the device. And here we can see that it's actually working well. So this one is the master. So but here we are oscillating between 85 to minus 100 nanoseconds on the network. So those precisions are really good and way inside the AES11 standards, those of you who know and use it. Okay, and then so that's it for the AES67 technologies, and then there's the RAVENNA thing. RAVENNA is using MDNS on top of that. That is, how do I find the different addresses, the different streams that are on my network? I can use a pen and paper, and it works well, but I might want to get something that is easier to use, and this would be for instance, MDNS. So every manufacturer, every protocol has its way of doing discovery. For instance, Dante with AES67 is using SAP, but with RAVENNA, it's using MDNS. So when a device arrives on the network, it asks the question, who is doing RAVENNA on the network and what are the streams on the network, and every device doing RAVENNA and having RAVENNA streams on the network is actually replying to the question with the information about how to get the stream SDP. So it's the same protocol as you're using at home for the printer to connect your printer on your home network. It's exactly the same, and it's working for really nice. And this is just to find the stream SDP. and this is used and codified by AES67. So this is the stream description protocol, and it describes the sending IP address, the name of the stream, the destination address, the PTP v2 domain, the port where it's sending the audio, the format of the audio. So here we see L24, 48 kHz, 8 channels, and a whole lot of different parameters. So this is like the identity card of the streams, and this is all the data you need to know to actually connect seamlessly to the streams. So transporting the SDP, there are a much different way of doing it. So as I said, you can use MDNS and another way of connection for RAVENNA, or you can use SAP if you're doing Dante, or you can even use copy and paste for some devices. So let's do some. So I have on my network, I have another devices that I'm using a lot, which is the Montone from Direct Out. So here it is, and I want to connect a RAVENNA Huawei stream to my Montone. So it's actually really easy. I can choose the RAVENNA session, so I can connect it the RAVENNA way, or I can connect it using the manual configuration. And to do that, I will go on my host page, choosing one source, download the SDP, open it with a text editor, copy, paste it to the Montone. Actually it's not a copy paste, so using it to a manual configuration. So let's do it the other way, so copy and pasting will work. So I have just the stream blah blah blah, and I have the SDP, so here it's already written, so I can copy it, here. I can go on the receive time of my OS, add a new receiver, manual configuration, and here we are, and it's receiving. So as easy as copying the SDP and pasting it in another device, or by using the Montone, it's actually simpler or different. I'm using 239.11.11.35, so I can receive it using a manual configuration. So okay, like that, only on port 1. Okay. And I'm receiving it. So I just use the same here, you see. So it's not the same name because I didn't put the actual name on the on the stream, but it's receiving the correct stream, so I can change the name here. Or whatever the name, and here it is. So those are two different ways of configuring the connection, RAVENNA connection, and also AES67 manual connection using SDP. So let's see how it works with Dante. So with Dante, there's a few tricks to know. So the first thing is that, okay, my Dante is properly configured to the right clock. So I will go to my device and I will go to the AES67 config tab. So if you have a Dante device and it can do AES67, it will have this tab. If it doesn't do, or the firmware is not updated or whatever, it doesn't have this tab at all. So you have to enable it, and you have to choose a multicast prefix so that your Dante multicast AES67 multicast address are constrained in a multicast subnet. So it's a weird choice from Dante, but whatever. So you have to know it. It's 67. Then, if I want to receive a stream, I can choose whatever stream I have, but you see that the multicast address is not the right one. So I will go to my OS. I will go to the source and change that to 67. This way, I have a multicast address that is compliant to what is expected by Dante. And so now, here it is, 239.67.1.1.155. I can receive it. So there's a little remaining from before, so let's try another one. And let's put another address. So .67.5, .67.5, here it is. And it's working. So it's quite straightforward. You just have to remember to put the correct number in the multicast address, so you cannot rely on the automatic scheme that is used by most RAVENNA devices. But you can do that. You can do that manually, and you should use a manual configuration anyway when doing Dante AES67 to RAVENNA. And the other way around is directly using the device configuration parameters and adding a multicast flow. So you add a multicast flow, you choose it to be AES67, and you see that here you can only have one multicast flow, one channel per AES67 multicast flow. So you can add one, and you click create. And then when you go into the transmit, you see that I have a bunch of AES67 sessions already, and just the one I just created here, which is number 29. So you can only create at most 32 different streams using AES67 and Dante. and this will be stream 29. So when I go creating a new sync, I can try to find it. So it begins with SAP, EXbox, and 29, and this one I just created. So because my device, my merging device here is doing SAP as well, so it's working right out of the box. If you have a device that doesn't do SAP, you can use other softwares like RAV2SAP, etc. I will present them tomorrow. If you're brave enough to be at the presentation tomorrow or to look at it later using the replay feature of YouTube. Okay, so this was it for the Dante interoperability demo. So one more thing I wanted to show you is the PICs. So at AES, we created a PICs repository where every device is, so every, that right now, so it has just been created like some weeks ago, so there are, not every AES67 device is on the PICs document right now, but we have here the emerging technologies one. So I can choose, for instance, the ASIO. And so we can see that the ASIO is capable of doing Multicast and Unicast. That is, the QoS is fully configurable. That the sample rates can go up to 96 kilohertz, etc. That it can do SAP, MDNS, that it has a loose packet transmit time. So this is because it's the ASIO driver, so it's a software driver. So the time between the packets, even though it should be exactly 1 millisecond, for instance, it cannot be exactly 1 millisecond because the software is limited by the power of the computer, the jitter buffer that is large, and the ST211030 compatible, etc. I can choose some other device to compare. So I can use one device I know. So a Yamaha device, for instance. And I can see that this one doesn't do 44 kilohertz or 96 kilohertz. And you can see that the packet spacing is strict and small. So for instance, this device and the ASIO driver that we had before would not be compatible, because when you have a loose packet spacing, you should have a large jitter buffer. So with the different PICs, you can have different ways of knowing if your devices will be actually compatible or not using AES67, because there are much different ways of there are many optional configuration or optional parameters in the AES67 protocols, and so in the end you can have different AES67 implementation that may not run perfectly one with each other. So Tibor, you had one more question. Don't you run the risk of auto-assigning, changing the multicast IP address attribute? So if you have a device that changes the multicast address attribute compared to what you just configured, it's either an old device or it's a buggy device. It shouldn't happen. And if you have one example of one manufacturer that told you it's his way of doing things and it doesn't consider that a bug, I would be pleased to have a chat with him and to understand why he thinks that way. So now in a typical working environment, you don't run the risk of auto-reassigning, changing the multicast address after a reboot. If it happens, it really is a bug. Okay, so that's it for today. I will stay a while if you have any more questions. Thank you for following this presentation, and don't remember it's available on replay if you want to watch it again. If you have any question, you can ask it in the comments later, or just reach me by email. Me or actually anybody who does AES67 or RAVENNA. It's always useful to have the return from the users or the wannabe users on what they understand and what they expect, and what we should focus our presentation on, so that the information is clear and goes through easily. Thank you.